Number 20, we're going to convert values of Kc to Kp. Remember, Kp equals Kc times RT raised to the delta n. So we're going to start with number 1. Kp is what we're going to calculate because we are given our Kc. So I'm going to fill in the values we know. We have our R value of 0.08206. Our temperature needs to be in Kelvin. This is 400 degrees Celsius. Add 273 to that, and that would be 673 Kelvin. And that product needs to be raised to the delta N. Now here I have 2 moles of gas on the product side, and I have 4 moles of gas on the reactant side. So that would need to be raised to the -1. And I may have just said raised to the -1. It's to the -2 because 2 minus 4 is -2. So that gives me a Kp value of 1 point, and let's see, I have 2 significant digits here. So 1.6 times 10 to the -4. So for number 2, I would also be calculating my Kp. I'm going to fill in my Kc value of 50.2, my R value, which is my constant, times my temperature. So here I have 448, and I need to add 273 to it to make it Kelvin. And that is 721 Kelvin, so that's going to go in here. I'm going to raise that to the delta N. Now in this reaction, I'm not given phases. I think I'm going to insert that all of these are gases. Here I have 2 moles of gas on the product side, and I have 2 moles of gas on the reactant side. So my delta N is 0. So this means my Kp is 50.2. In number 3, we are given our Kp and we need to calculate Kc. So in this case, I'm going to put my Kp here. Kc is what I'm looking for. So I will solve, here's my R. My T is going to be 298 Kelvin because I am at 25 degrees Celsius, and I need to raise that to my delta. My delta is 0. I have no moles. Wait a minute here. Now I see it. Here's 10 moles of gas on the product side. I have no moles of gas on the reactant side. So that's going to be raised to the 10th. So then in order to solve for this, I'm going to take my 4.08 times 10 to the 25, and I'm going to divide it by all of this so that my Kc is equal to let's see, we have 3 sig figs here, 5.34 times 10 to the -39. So notice in the calculator we have an E here. Make sure you are not actually typing times 10 raised to a power. On this particular calculator, this is a TI-84, I use the second key and then the comma. That gives me an EE. So that's how you do scientific notation for this calculator. For the fourth one in number 20, I'm given my Kp value, so I'm going to start with that, and that is going to be equal to Kc, which is what I am calculating. Temperature, here I'm given a temperature of 50 degrees plus 273. That would end up with a value of 323 Kelvin. Now I'm going to raise it to the change. So I have 1 mole of gas on my product side and none on my reactant side. So I'm going to raise that to the first power. Now in the calculator, I'm going to take 1.122 and divide it by the product. So I'm going to use my parentheses here. So I get a value of 0.0046. Now I have 3 sig figs here, so I really should end with 3 sig figs, 460 for my Kc. Number 21 is going to be solved very similarly to number 20. So Kp is equal to Kc times RT raised to the delta N. So here we're given a Kc at 25 degrees Celsius. So we're going to calculate our Kp by filling in the values we have. We need to figure out our delta N. So here we have 2 moles of gas on the product side and 2 moles on the reactant side. So that's going to be raised to the 0 power, which means our Kp is going to be equal to our Kc 4.7 times 10 to the negative 2. For the second one, again, we're given, this time we're given a Kp. So again, we fill in what we know and we will calculate what we don't. This time we do not know our Kc. Our temperature is 500 degrees Celsius, so we add 273 to it to make it Kelvin. We need to raise that product by the delta N. So we have 2 moles on the product side here, and this time we have 3 moles on the reactant side. So I need to raise that to the negative 1. Now that makes our Kc equal to, and I'll work this out in the calculator for you, showing you the keystrokes. So I start with my 48.2, divide it by, in parentheses, I need to put my 0.08206, multiply it by my temperature, which is 773. Then I'm going to raise it to a power. I'm going to use this caret button right here. -1. So I get a Kc value equal to 3,069. Now I started with 3 significant digits. I really should only have 3 significant digits here. So 3,070 would be 3 significant digits. 3 are significant and this one is not. You could put that in scientific notation if you feel that that is ambiguous. And the third one, again, we're given a Kp value, 5.09 times 10 to the negative 44. We do not have Kc. We will calculate that. So I put in my R value. T is going to be 298 Kelvin because I have 25 degrees Celsius. And I need to raise this product to the delta N. Here we have 6 moles of gas. And we have no moles of gas on the reactant side, so that's going to be raised to the 6th power. So in the calculator, I put my 5.09, then I use my second function and this comma, which gives me the EE. That gives me my scientific notation. I'm raising that to the negative 44th. Then I'm going to divide that number by the product of my R value times temperature, and I need to raise that product to the 6th power. So I get a Kc value equal to 2.38 times 10 to the negative 52. Now just take note that the Kc value is very, very small. Times 10 to the negative 52 is a very small number. So this is likely to be a reaction that heavily favors the reactants instead of the products. And in number 4, we're given the Kp again, and we need to calculate the Kc. We're given the, we know the R value. Our temperature is given, so we have 60 that we will add 273 to and get the Kelvin value of 333. We will raise that product to the change in N. So we have 1 mole of gas on the product side and none on the reactant side. So that will be raised to the 1st power. So our Kc value will be found by taking 0.196, dividing it by the product of our R value and the temperature. Now you can raise this to the 1st power, or if you remember your algebraic techniques, raise to the 1st power is just going to be the product itself. So the Kc value is equal to 0.00. I have 7. Let's see, we have 3 sig figs, 717. Number 22, what's the value of the equilibrium constant expression for the change of water going from liquid to gas at 30 degrees Celsius? Well, this assumes that you have a way to look at the vapor pressure of water. So I'm going to insert that information here. So the vapor pressure of water at 30 degrees Celsius is 31.8 torr. So if you're given that information, now you can calculate the equilibrium constant expression for this change. So Kp is going to be dependent on the pressure, the partial pressure of the gaseous water. That's the product. There is nothing on the reactant side to divide by, so it would be divided by 1. So if I convert this torr into atmospheres, because we do need to use our standard units here, so 31.8 torr, remember it's 1 atmosphere for 760 torr, then I have 0.0418 atmospheres. So the Kp value here would be 0.0418. Number 23, write the expression for the reaction quotient for the ionization of HOCN in water. Well, if we do this, then this hydrogen here, this is an acidic hydrogen. The form is called the hydronium ion, and we'll talk about that in the next module. And we would form the counter anion. So this is what we would have. So our products would be the concentration of the hydronium ion times the concentration of the anion divided by the concentration of the weak acid itself. We would not have a concentration of water because that would be considered liquid at that point. Number 24, we're going to write the reaction quotient expression for the ionization of ammonia in water. Now again, I'm not sure I would be asking this at this point. In the next section, absolutely. But I don't think I would ask you this one here. So you can take this information and just hold on to it. But what we're going to do is we're going to transfer a proton from water to ammonia, and we're going to make the ammonium ion. Then we're going to be left with hydroxide ions. So when we create the reaction quotient here, we're going to be dependent on the concentration of the ammonium ion as well as the hydroxide ion. And we're going to divide that by the concentration of ammonia. Now water here is going to be liquid, so it will not count in the reaction quotient.